All right, so welcome to this STAT 313 course. I'll be your instructor. My name is Professor Indranil SenGupta. Let me share my screen to see the syllabus. So you should be able to see this syllabus in your bright space. So this will be STAT 313 and the course objectives. So the primary focus for this course would be to study the estimation, hypothesis testing, confidence limits for some normal and its variance. We'll see as we go along in this course what it means. And so we'll be learning some statistical inference, some how to build the confidence interval, how to find the maximum likelihood functions, and many things related to that. So this course has a prerequisite, so it's STAT 311. So if you did not take STAT 311 before, please let me know because I'll be counting on that course. Because there are a lot of materials for this particular course which are heavily dependent on STAT 311. For instance, I'll be assuming your knowledge on the basic discrete distributions, such as binomial, Bernoulli, Poisson, or the continuous distributions such as normal. And I think that should be pretty much it. I think I'll give some more details as soon as we start the review. I'll do a little review at the beginning. But there are some distributions which you need to know from STAT 311. Okay. There is a textbook. There is a textbook for this course. So that is Introduction to Mathematical Statistics. This is, and I'll be using the 8th edition, and all the homework problems will be assigned from this 8th edition. So I'll be expecting that you have this book. Okay. Now, since it's an online asynchronous lecture, so all the announcements will be communicated via Brightspace. So please, I'll encourage you to check the Brightspace fairly regularly. And also, I'll be posting all these videos in Brightspace. So if you found this video, that means you're already in Brightspace. So that's good. Or probably you'll be getting email notification, and if from there you have to find the link. But I would definitely encourage you to log into Brightspace and check this course regularly. I'll have office hours. I forgot to mention. So I'll have office hours every week. And also, if you cannot make those office hours, you're welcome to have an appointment with me. Just send me an email with your preferred time. I'll try to incorporate that in my schedule. Also, I'll send a link of the office hour to you. So I'll probably I'll post it on the Blackboard or on the Brightspace as well, so you can check or you can communicate with me through that Zoom link during the office hour. Now, every week there will be 1 or 2 homeworks. And in the homeworks, the due dates will be listed. Now, since this is a summer course, it's pretty fast-paced in the sense that every week we'll be covering 1 or 2 chapters. So there will be homeworks, but again, I'll try to keep it 1 or 2 week. Homeworks will be posted on Brightspace as well. Regarding the exams, I'll discuss later, but first let's deal with this schedule. So again, this is a very tentative schedule. I don't know if we can cover all these chapters, but the idea is we'll start this week with some review material as well as some basics from chapter 4, which is statistical inference. And then we'll be dealing with statistical inference and limit distributions in the second week. And then from there, we'll talk about the maximum likelihood methods. And finally, we'll talk about the optimal testing of hypotheses. And if time permits, we'll have the inference about normal linear models. Okay, so that's a very brief schedule. Don't worry about it. We'll be discussing chapters as needed. For instance, if you see here, we have chapter 4, chapter 5, chapter 6 and there is chapter 7 missing. So there is no chapter 7 if you're following the textbook. And then we do 8 and 9. And the 9, I don't know how much we'll be able to do because it's at the very end, but we'll try to cover most of chapter, the first 4. Okay. Now, regarding the homeworks, as I already mentioned, that there will be homeworks posted on Blackboard, on Brightspace, and you should be able to access the homework. And you have to, there are two options. You can either upload the homeworks on Brightspace, or you can send, just take a photo or scan your homework and send it to me by email. My email is listed at the very top. So right here is my email. So it's my first name dot my last name at hunter.cuny.edu. Okay, and then there are exams. So there will be two exams, two midterm exams and one final exam. So the midterm exams, all the exams, midterm and final, will be take home, but it's time limited, meaning that you'll have to answer the exams within 2 hours. So the exams will typically start around 8 a.m. Well, so the way it'll work is um, I'll post the exam on the Brightspace, and the exams will be visible at 8 a.m. on a certain day. Okay, and I mean, you have to answer the exam and send me the scanned copy by 10 a.m. So it's a time-limited exam. Okay, and also there will be a final exam, and the final exam is scheduled on July 8. And the procedure is the same. So you'll be seeing the exam on July 8, the final exam, at 8 in the morning. You should be able to access it in Brightspace, and then you should be able to send the exam back to me by 10. So grading, as you can see, there are equally weighted homeworks and tests and final exam. So homeworks will have 25%, each midterm will have 25%, and then there is a final exam, which is 25%. There are statements regarding the academic integrity, disabilities, and other things in this syllabus. So please read it. And if you have any question, please send me email or ask me questions regarding the regarding anything related to the syllabus by email, or you can send me an appointment. If you cannot make the scheduled appointment for the office hours, you can send me an email, and we can always schedule an appointment for you. Okay, but that's all about the syllabus. Okay, so now let's get started. So we'll be first, let's try to do a review of the material. So let me just stop sharing this screen. Let me change the camera. Okay. So this is the STAT 313. It's lecture 1. So I'll be doing some review, and once again, I'll be assuming the background from STAT 311, which is the prequel of this course. Okay, which is basic probabilities and statistics. All right, so just a very brief review. So there are two kinds of distributions. One is continuous, and other one is discrete. What is a continuous distribution? Where a random variable x takes uncountably infinite values. For instance, x can take any value in the interval, say 0 to 1. Okay, And what is a discrete distribution? So here is x takes finitely many, or well, finite or countably many value. Sorry, countably infinite. Many values. What are some examples? So for instance, x can say take say 0 and 1. That's a perfect example of discrete distribution. That's the example of when x takes finitely many values, or it can be say x takes a value 0, 1, 2, 3, or so on up to infinity. So it's a countably infinitely many value. So x in this case is also a discrete distribution. Now, this is something we have done in stat 311. Now, for the discrete distributions, probability is characterized by the so-called probability mass function. For the discrete case. And for the continuous case, what is probability mass function for a discrete random variable? So very roughly, so if the random variable x takes a value, I don't know, k, so we write this as little p of k. Okay. So, and suppose this x takes, so suppose this k can be 1, 2, and 3. So then these are the three values, probability mass function. It's just an example. One important remark is for the case of the probability mass function, it exactly picks up the probability. However, for the case of the continuous random variable, we characterize this by the probability density function, which is not exactly the probability, but if I want to compute, say, probability of a less than x less than b, I simply compute this by integrating the probability density function. So this is fx is like a probability density function. Incidentally, in the previous case, this probability mass function is basically this p. Okay, so we compute this. And whatever we get, that gives you the probability of a continuous random variable in certain range. Okay. Some examples of discrete random variable. Binomial or Bernoulli. Binomial. Geometric. Or Poisson. I'll be assuming that you know all these distributions. So if you are not familiar with this, please go back to your course notes for stat 311, because these distributions will be, I'll not cover. I'll be assuming that you already know this. Or simply search in Wikipedia or somewhere, that should be fine. Just get yourself familiarized with these four distributions. Okay. For the continuous case, random variable, I'll primarily assume three distributions, which I'll not cover. So uniform distribution, exponential distribution, and finally the normal. Okay. All these distributions you should have seen in stat 311, and once again I'll not cover. So, but that is pretty much it. Whatever other distributions I need, I'll mention, and we'll talk about it. Okay. So all you have to know is there are two kinds of distributions. One is discrete, one is continuous. For the discrete case, the random variable takes only a finite or countably infinitely many values. For instance, in this case, so for Bernoulli case, it can only take values 0 or 1. For binomial case, it can take a certain number of values, finitely many values. For Poisson and geometric, it can be infinitely many values. Okay, by that I mean that it can be 0, 1, 2, 3, so on, countably infinitely many values. Uniform distribution, exponential distribution, especially normal distributions. So these are super important, and I would recommend you to check your previous class notes or just search in Wikipedia to get yourself familiarized with this 4 plus 3, 7 distributions. Okay. All right. Now with this, we can get started. So let's start. So first thing we'll be dealing with here is the random sample. So we are still doing some review. We are not in any particular chapter, so review continues. But what I mean by that is like the previous, what I wrote here, it's a review from Stat 311. Okay. And now I'll be doing some review of some material which you probably have not seen. So I don't know if you have seen it. You may or may not. So, but I'll be doing some review on that too. So let's start with the definition of a random sample. If, let me just write this, if the random variables so if the random variables by the way, so whenever I'm writing a random variable, I usually write with capital X, but capital X is very hard to write. It's sometimes very confusing. So this would be my capital X, and this will be my small x throughout this course. Okay, so this is a random variable, and this is a value of a random variable. Okay, so you'll you'll get yourself familiarized with this because I'll be using this a lot. But x, whenever you see this x, this really means the random variable x, and this little x is the values of the random. Anyway, okay, so if the random variables, so suppose we have bunch of random variables n, x1, x2, all the way up to xn are independent, and identically distributed. What does it mean? So each of these x1, pick your favorite x's from here, pick your favorite another x from here, they are independent. Okay, so they are independent and they are identically distributed, meaning that so what is identical distribution? So distributed, so that means each of these x follows the same distribution. So if this x1 follows a normal distribution with mean 1, variance 2, same is true for x2, same is true for xn. Okay, a way to abbreviate this is IID. Okay, so it's independent I and identically distributed, so that is IID. So we will be using this abbreviation a lot, so it's good to know this. So suppose this x1, xn are IIDs. Then we say that these random variables, that means what I wrote here, constitute a random sample. That is the thing I'm trying to define here. Random sample of size n from a common distribution. So what is the definition of random sample? It's basically an IID. Okay, so if I have bunch of like a random variables, so maybe n random variables, so which are IIDs, then we call that a random sample. Okay. Okay. So now we'll have, I mean, in this course we'll be using lot of analysis for this random sample. So it's important that we understand this carefully. So let's first try to understand the sample mean. Okay. So suppose that x1, x2, xn are IID with common mean equals mu and variance equals sigma square. Let me try to explain this. So this each of these x's, so we have bunch of x's. So we have x1, x2, x3, xn. So this each of these x's, they are following the same distribution and they're independent, right? So x1, xn, so everything are independent. Now x1 has a distribution. It's coming from some distribution. We are assuming the mean of that distribution is mu and variance is sigma squared. Okay, x2 is coming from some distribution, same as x1. So that means the x2, the distribution that x2 is coming from is having mean mu and variance sigma squared. And same is true for xn. So everything here, x1 through xn, each of these will have the common mean mu and common variance sigma squared. Okay, okay, so this is not hard to understand now. The sample mean, so we are trying to define this. The sample mean is defined as x bar. So I'll write this x bar equals 1 over n summation I from 1 to n xi. That's the definition of sample mean. Okay, so sample mean is denoted as x bar. Okay. Please note that this is not really the the mean from which it's coming from. For instance, so suppose I give you, I'll give some examples later, but suppose we have a bunch of numbers. So by that I mean, so say this x1 is suppose in a classroom we have 10 students, and this we have reasons to believe that the student population, the height of the student populations, it follows certain normal distribution. Then x1, x2, xn, or in this case x10, would follow certain normal distribution, right? So but their average, their average, it may not be, this normal distribution. So suppose we know that this x1 follows a normal distribution with mean, I don't know, like maybe what is a good average for a classroom? So maybe 5 foot, 5 foot 4 inches, so 5.4 feet, and some sigma squared. I don't know, sigma squared. So suppose we have this. Suppose x2, another student's, the second student's height, it's 5.4 feet, sigma square. X3, the third student's height, it follows 5.4 feet, sigma squared. So suppose we have reasons to believe that these 10 students, they are for their heights, it follows, they're drawn from the same normal distribution. Now, when you actually observe the highs, meaning that, so when you look at the height for the first students, x1 maybe, I don't know, it's 5.9. It can be just any number from this. X2 can be, say, 3 feet. X3 can be, say, 5.4 feet, say. And X10 can be maybe 6 feet. Okay. So what I'm talking about here, so this X bar, which is the average of 5.9 plus 3.0 plus 5.4 all the way up to 6 divided by 10, because there are 10 students. So if I compute this number, whatever I get, that is my X bar. it may not be same as 5.4, which is mu in this case. So this 5.4 is mu because that is the mean of the distribution from which it's drawn. So what I'm saying is, suppose, suppose this number after calculating, writing suppose because I have a dot dot dot, meaning that I didn't clarify what the other numbers are. But suppose we get this number to be, say, 6 point, or maybe let's see, 5.3. Okay. Then your x bar is 5.3. What is mu? Mu is 5.4. So what we are saying is that this mu and x bar, they are different. Mu is the mean of the common distribution. X bar is the mean of the sample, of this 10 sample when you really observe it. If you have 10 other samples, it may be different. Okay? They may be from the same distribution, but it may be different. Okay. There is another name which is commonly used here. So this mean is called the population mean. And this is called the population variance. What is the population mean or population variance? So just look at this example. Here, 5.4 is a population mean and sigma squared is a population variance. What is sample mean? Sample mean is this number, x bar. Okay, they are different. Okay, since I defined the sample mean, let's define the sample variance too. So what is the sample variance? So now it's very easy to understand. Sample variance is something like when I computed the average of this one, that is called the sample mean. If I compute the variance of these numbers, it's called sample variance. Okay, so let's define it. um, okay, I'll define it for the next one, but let me just do two more computations. So let's compute the expected value of x bar. Okay. So here is my x bar. So let's compute the expected value. How do we compute it? This is going to be expected value of this whole thing, 1 over ni from 1 to n xi. Now, you know that expectation can go inside. So it's 1 over n I from 1 to n e of xi. What is e of xi? It's given to be each of these xi's are drawn from a population with mean equals to mu and variance equals sigma square. That's what we know, right? So that means what is the expectation of xi? That means it's a mean of xi, which is mu. This is I from 1 to n mu. I'm adding n number of mu's, so its value is n mu. So what I get is mu. So now another very nice result, what we obtain is e of x bar is mu. So expected value of the sample mean is mu. Okay. What does it tell me? So suppose I'm talking about a class with 100 students, for instance. Each student follows a normal distribution for each student's height follow a normal distribution with the mean, say 5.4 and variance a sigma squared. Okay. Now, suppose each time I'm collecting a sample of 10 students and I compute the sample mean like this one, like here I found 5.3. Maybe if I choose 10 different students, because this class may have 100 students. So here just 10. Maybe if I choose 10 other students or 10 different students, so this number will be different. Okay. Another 10 students, this number will be different. What this is saying is now we have a random number for x bar, right? So every time I pick up 10 students, it will give me a corresponding number. What is it saying? So this result, it's saying that the expected value of that random number x bar is mu, which is same as 5.4. Okay, so that means it's this number individual may not be 5.4, but the expected value as a random variable would be mu. All right. This has another thing, but I mean, this is called that we say that X bar is unbiased for mu. Okay. When so what is the definition of being unbiased? So that means if you have two random variables, so if you have a random variable and that random variable's expectation is this mu, then we say that this X bar is E of X bar is mu, then we say X bar is unbiased for mu. Okay. All right. Another thing, so this is the first one, and the second one is from this same result. So we have X bar equals, once again, sample mean equals 1 over n summation I from 1 to n xi. Here, let me write an aside. And you should have seen this in a Stat 311 course. This goes like this. So suppose we have, say, x1 and x2, two independent random variables. So x1 and x2. So this is a notation for independence. This perpendicular, it means x1 and x2 are independent. So we know that if we write this E of x1 plus x2, so this is E of x1 plus E of x2. We have used it. Okay. What about the variance if x1 and x2 are independent? That also follows this relation. So it's really variance of x1 plus variance of x2. Provided, please note that provided this x1 and x2 are independent. It's not true in general. Okay. What about variance of ax1 plus bx2? Well, this is, in this case, when x1 and x2 are independent, it's h squared variance of x1 plus b squared variance of x2. Okay. Now, I can think about this one as, say, 1 over n x1 plus 1 over n x2 plus 1 over n xn. There are n terms added up, right? So what would it, and note that this x1, x2, xn, they are coming from some IID. What is the definition of IID? So that means they are independent and identical distributed. Independent part says that each of these x's are independent. So that means variance of x bar would be simply 1 over n squared variance of x1 plus 1 over n squared variance of x2 plus 1 over n squared variance of xn. Since x1, x2, xn, IID, they are independent. If they're not independent, there is another covariance term at the end. Okay. Now, what is the variance of x1, variance of x2, variance of xn, etc.? So they are the variance. Their variance is given by sigma square. It's written right here. So xi's are drawn from a population with mean mu and variance sigma square. So the variance of each of this is sigma square. So it's 1 over n squared sigma squared plus 1 over n squared sigma squared all the way up to 1 over n squared sigma squared. How many terms are there? There are 1 through n terms. So there are n terms. So it's n times 1 over n squared sigma squared. So the result is sigma squared over n. So variance of x bar, let me just box it, variance of x bar. So that means this the variance of sample mean is sigma squared over n. Okay. One important thing out of this one is basically this result, what we obtained here, is not as nice as this result. Why? Because from here we have x bar. It's we'll see. I mean, for the next one. So I mean, this result will create some problem for some sample variance discussion. We'll do it later, but for now, let's keep it simple. Let's these are two nice results. So for the sample mean, this is the expected value. This is the variance. Okay. So far, these are the two results. Okay. Now next, And sample mean sample mean is an unbiased estimate. It's called the unbiased estimator of the population mean. Let me just write it here. So this another version of this one is it's called the sample mean is an unbiased estimator of population mean. Now you may ask question, what do I even mean by estimator? Please don't worry about it. I'll be clarifying all these things in the later section. I just wrote this because this is a very important result to remember. So this result is known as sample mean is an unbiased estimator of the population mean. So what is an estimator? We'll go over this in details. Okay, but at least you can understand that this word unbiased is coming from the expected value of x bar is mu. Okay, and x bar is the sample mean, mu is the population mean. All right, next. Sample variance. So the previous one that we discussed, it was a sample mean. So now let's define the sample variance. Okay. This is defined in a little different way. So sample mean is this one, which is pretty intuitive. It's basically you give me 10 number, I'll add those 10 numbers and divide by 10. If you give me n numbers, I'll add those 10 numbers, divide by n. So that's my sample mean, right? Sample variance is little different. It's not simply that give me 10 numbers and I'll compute the variance of 10 numbers and that's it. So it's define a sample variance by s squared equals, note this, n minus 1 summation I from 1 to n xi minus x bar squared. Okay, what is that? So that means let's go back to the previous example. So now if I have 10 heights, okay, so heights of 10 students in the class. In order to compute the sample mean, I simply add these 10 heights, whatever I observe, and compute divide by 10 to get this, right? Sample variance, what I have to do, I have to first compute x bar anyway, because this x bar will be used in this expression. Then for this example, it will be s squared would be, for the previous example, would be I'll divide by, so if there are 10 numbers, I'll divide by 10 minus 1, that is 9. And now I'll do the following. So note that the first number has 5.9. So it's 5.9 minus 5.3 squared. Second number is 3.0. So 3.0 minus 5.3 squared. Where this 5.9 is coming from? That is my x bar. That is what I wrote before. Then plus 5.4 minus 5.3 squared all the way up to 6.0 minus 5.3 squared. Whatever I compute this, or whatever number it's coming coming out to be, that is my s squared. Is that clear? So once again, so there are 10 numbers. I didn't write 10 numbers. I really wrote 4 numbers, but suppose that's why I put dot dot dot. Suppose there are more numbers, and suppose the x bar is 5.3. So how do we compute s bar squared? There are 10 numbers, so I divide by 9. Note this carefully. When I compute the sample mean, I divide it by 10 actually. Okay, but here for sample variance, I divide by 9, one less. And then what do I do? So I take individual numbers like 5.9. I subtract from the sample mean x bar and squared and add those. Whatever comes, that is my sample variance. Okay, that's the definition. Okay. I hope the procedure is clear. Now, the big difference between the sample mean and population and sample variance is, for sample mean, we are dividing by n. For sample variance, we're dividing by n minus 1. There is a reason for that. The reason is actually encoded here, what I was pointing out before, that this denominator is not really good. So we are going to make it good, whatever that means. Okay. All right. Let's see. Let's compute the expected value of s squared. Okay. So what is the I think we have done this exercise before. So after defining the sample mean, what we did before is we computed e of x bar. So now we defined s squared. So let's compute e of s squared, expected value of the sample variance. Okay. So that is going to be e of the whole thing, this whole mess. So it's 1 over n minus 1 summation I from 1 to n xi minus x bar squared. So it's very difficult to write this x bar because I'm using anyway a bar with x. But anyway, okay. So let's see. For those, actually for everyone, you should be familiar with this one. So expected value can be distributed over each term. So I from 1 to n. So this is going to be e of xi minus x bar squared. Okay. This number, let's try to simplify it. So it's going to be 1 over n minus 1. So it's I from 1 to n. So this is e. Let's FOIL it out. So I have xi squared plus x bar squared. So x bar squared minus 2 xi x bar. Right? So now let's compute this quantity. So that what we have is this is going to be 1 over n minus 1. So first term, so each of these xi's would follow. I think I'll be skipping some computation. So I from 1 to n. This is very similar to what we have done for proving that this variance is given by e of xi squared. Let me just, I'll probably assign this as homework. Otherwise, it'll be taking longer time. Minus n times e of x bar squared. Okay. It's really not really hard to see from here, but I'll probably assign this as a homework. It'll take some time of computation. So okay, so from here to here we get, and then let's plug in. Now it's very easy. So now we just plug in the values. So meaning that the first one. So let's see. So what is e of xi squared? So this is e of xi squared minus e of xi squared, whole thing squared, is actually the variance of xi. If you recall your stat 311. What is the variance of xi? So again, xi's are drawn from the samples which are xi's are drawn from population which has variance sigma squared. So sigma squared equals e of xi squared minus, and they have mean mu squared. So e of xi squared is sigma squared plus mu squared. I got this number. What is e of x bar? E of x bar we have just computed. E of x bar we found it to be mu. So then this term e of x bar squared, once again variance of x bar is really e of x bar squared minus e of x bar whole thing squared, right? Variance of x bar we have computed before, it's sigma squared over n. This is e of x bar squared, that the quantity we are looking for, minus this is mu squared. So e of x bar squared from here would be sigma squared over n plus mu squared. Now plug everything back, meaning that plug this one and this one here. So I'll plug this one here and plug this one here. What I get is 1 over n squared, 1 over n minus 1. So here it's a summation I from 1 to n. This quantity is sigma squared plus mu squared minus n times this quantity is sigma squared over n plus mu squared. Okay, this summation is independent of I, so this is going to be 1 n minus 1 n sigma squared plus n mu squared minus n times this one is sigma squared minus n mu squared, right? So something will get cancelled. So this gets cancelled. So what I have is n minus 1 sigma squared. So this is just sigma squared. Okay. My final this computation, you can forget about everything about this computation. What you have to remember is the following. So you can remember the following result. So what we found is the E of S squared is sigma squared. Okay. So once again, this means that what I wrote before is true for the sample variance the way we defined. So that means we say S squared is unbiased for sigma squared. So sample mean, sample variance, when you take the expectation, it's sigma squared. Okay. Why it's so important? Because it's little not intuitive, because we are dividing, I mean, intuitive one would be if you are dividing by n for this computation, but here you are dividing by n minus 1. So what's going on? So suppose, so suppose you started off with, say, s prime squared. So suppose is the intuitive one, which is 1 over n I from 1 to n xi minus x bar squared. The intuitive way of computing the sample variance. By the way, if you look at this one, what's the relation between this one and s squared? So I can always convert this one in terms of s squared. So I can write this as, I need a n in the denominator. So let's write n minus 1 I from 1 to n xi minus x bar squared, and then multiply with n minus 1 over n, so that I have this expression, right? The advantage is now we have n minus 1 over n, and this quantity is s squared. This is nothing but s squared, according to our definition, because I'm dividing by s squared. So what is the relation between s prime squared, which is the intuitive way of defining the sample variance, and the sort of the convoluted way of defining sample variance, or the actually defining the sample variance? That's satisfying this relation. So what is E of s bar s prime squared? That's really n minus 1 over n E of s squared, and we have already found s so s E of s squared, right? So E of s squared is sigma squared. So it's n minus 1 over n sigma squared. So in fact, you found something strange. You found that this E of s prime squared, the intuitive way of finding the sample variance, is not unbiased, in the sense that its expectation is not sigma squared. It's sigma squared times something. It's n minus 1 over n is there. And hence, we make, just in order to make this term disappear, we divide by n minus 1. Okay. And then everything remains fine. And as we have seen, that this becomes sigma squared. All right, so this is a brief overview of the sample mean and sample variance. And I'll not probably compute the variance of sample variance. That's not required. So expected value of the sample variance is sigma square. And please remember, throughout this course, you'll be using this definition. So this definition is really, really important. So you're dividing by n minus 1 for the sample variance. You're dividing by n for sample mean. Okay, I'll assign some exercise so we can compute this with some numbers. Okay, so that is the first thing. Now, let's take a digression. So this is the first thing which you will be needing for studying chapter 4. These are new things, okay? So that's why I plan to mention this. The second thing, another background material. I'll be defining a couple of distributions, so which are sort of very useful for studying this course. So if you recall that the continuous distribution, continuous random variable, For stat 311, you had uniform, you had exponential, and you had normal. I don't know if you have covered more in this previous course, so what like stat, but anyway, I'll consider this as new distribution. So I'll mention some new distributions, okay, which will be relevant for this course. I'm just purely focusing on this course, okay. There are many distributions which are very important, but will not need all. So the new one that will be starting is gamma. The second one that I'll be mentioning is the chi-square. And there are the last one that will mention, at least last one in the sense that we might need some more distributions which I'll be adding whenever it's required, but at this point, the T distribution. So let me just briefly mention these distributions and some of the results related to that, okay? So let's start with the first one that I wrote. So that is a gamma distribution. So gamma distribution. And distribution is abbreviated using dBn. And gamma, you know that it's a Greek letter. It's okay. I'm assuming that you have some familiarity with the gamma function. If not, here is a very basic definition. So here is an aside of the gamma function of mathematics. Okay, so gamma of n is defined as 0 to infinity e to the minus x, x to the n minus 1 dx. This integral is a definition of gamma function. Okay. Why it's so popular? It's popular because it actually extends the concept of factorial. So the notation factorial can be extended with this definition. So for example, we know that gamma of n plus 1 is n factorial if n is positive integer. Okay, but remember that this definition is true for every n as long as n is not 0 or negative integer. Okay, okay, so it has a very nice property. Again, this is just from mathematics. So gamma of n plus 1 is n gamma n. Okay. Um, I don't know how many more properties you want to, for example, gamma of 1. So if I assume that this n is 1, so it's basically 1. Okay. Not only that, so there are ways to compute this for the fractions. Again, I'll not really go into that details, but because we'll not need it. So all I want to know is this notation. So by gamma of n, we mean this quantity. Okay. Once again, we are doing not a math class, it's a stat class. So this is sufficient to know. So now what is a distribution? So now a continuous random variable. So continuous random variable x has gamma distribution with parameter alpha bigger than 0 and beta bigger than 0 if its PDF. Remember, every distribution is characterized by its PDF, and this PDF is weird, but a little convoluted, but you don't have to memorize it. So fx is 1 over gamma alpha beta to the power alpha. And then what we have is x to the alpha minus 1 e to the minus x over beta. This is for 0 less than x less than infinity and 0 otherwise. So that is the PDF for the gamma distribution. Okay. Once again, you don't have to memorize it. So I needed this definition of gamma of alpha. So that's why I wrote it here. But this is other than that, it's just you can just treat it as a regular distribution. Okay. All right. Let's see. some properties. So expected value of X in this case is alpha beta. So there is alpha and there is beta. So that is the expected value. So for this distribution, for X follows gamma distribution, it has two parameters. So it's written as alpha comma beta. So for X satisfying gamma distribution with two parameters, the expected value of X is this one. And also it can be shown that the variance of X is alpha beta squared. Okay, we'll not spend much time on gamma distribution, but one very important thing which may be relevant is when for the case when suppose we take that alpha to be equals to 1, special case. Again, it's just a nice observation. You don't have to memorize or anything. So special case, if I take this alpha to be 1 and just let beta to be a free variable, then fx becomes, if you look at this one, gamma of 1 is 1. So it's 1 over beta e to the minus x over beta for x bigger than 0 and 0 otherwise. For those, once again, I'm assuming all of you took 311 courses, Stat 311. So this is a very common distribution in Stat 311. It's called the exponential distributions. This is really exponential distribution. Typically, when we write the exponential distribution, we had a parameter. So let me remind you. So exponential distribution is written as this lambda e to the minus lambda x for x bigger than 0, 0 otherwise. That is a typical exponential distribution, right? In this case, if you compare this lambda is 1 over beta, right? So with parameter 1 over beta, lambda equals to 1 over beta. Okay. So the special case when we have alpha equals to 1, then the gamma distribution is actually becoming an exponential distribution. Okay, it's just a nice observation, nothing more specific than that at this point. Okay, that's all about gamma function that I want to discuss. Now, next one. The chi-square distribution. Okay. Now, for those who took Stat 311 with me, I mentioned briefly in the class, but we didn't really study this in details. The way we defined, again, don't worry if you did not take this course with me, so it doesn't really matter, but one way to define this chi-square distribution is to take a standard normal distribution and square it. Okay, so that is one way of defining chi-square distribution, but here will be, I mean, that is okay, but that's a very special case of chi-square distribution. Here will be taking a more general approach, which will sort of encompass what we define. Okay, so it will have more degrees of freedom, sort of. Okay? So this is defined the following way. So it's a special case of gamma distribution where, remember, gamma distribution has two parameters. Show you. It has two parameters, alpha and beta. So I'll be choosing alpha to be r over 2, where r is a positive integer, and beta is 2, number 2. Okay. Why? There is a reason. I mean, it's a very important distribution, and you'll see why. Where alpha is r over 2, where r is a positive integer, and beta equals to 2. Okay. In this case, you can check that this looks like then fx, the PDF of the chi-square distribution, it looks like 1 over gamma of r over 2, 2 to the r over 2, x to the alpha minus 1, which is r over 2 minus 1, and then e to the minus x over beta, so it's minus x over 2 for x positive and 0 otherwise. So this is the PDF. So this is the PDF of chi-squared distribution. This is a Greek letter chi and then squared, chi-squared distribution. And note that this chi-squared has a parameter in the sense that so this chi-square actually has only one parameter. So it has r, right? So other than r, there is no parameter. So it's sometimes written as chi-square r. Okay. What is the expected value? So E of x. So if x follows chi-square distribution, what is E of x? We have this here. It's a special case of the gamma distribution. So here it's alpha times beta. So I basically have to write alpha times beta. So it's alpha times beta, which is equal to, in our case, it's r over 2 times 2, right? So it's r over 2 times 2, which is r. So expected value of chi-square distribution is r. And what is the variance of chi-square distribution? So it's also alpha beta squared. That's variance of x is alpha beta squared. So in this case, it will be r over 2 times 2 squared. So it's 2r, right? So this is the mean, and this is the variance of chi-square distribution. Okay. We'll be using this chi-square distribution a lot, but here let me write, a theorem. We'll not use this in a theoretical tool. We'll be mostly using the tables. But here is a result, a theorem that is, I'll not prove it, but it's important. Okay. Let x1, x2, x1, x2, xn be independent random variables. Okay. Suppose that for each I, xi follows some chi-square distribution with parameter ri for I equals to 1 to n. So that means I'm saying x1 is following the chi-square with r1, some number r1. x2 is following chi-square with r2, and so on. xn is following chi-square with rn. Very important thing. I'm saying it's independent. I'm not saying they are identically distributed. Actually, they are not. They are following chi-square distribution with different parameters. So it's IID if we can take, if we can say that each of this xi follows chi-square with certain, like the same r. Okay, but here I'm assuming that maybe they are different r's. So there, I'm not necessarily assuming that they are IIDs. I'm just assuming that they're independent. Okay, let us consider random variable, which is a sum of all these random variables. So that means sum of i's, xi's. It's a natural question. What kind of distribution will this y will have? And the amazing result is then y follows a chi-squared with sum of ri, I from 1 to n. Okay. It's a beautiful result. We'll not prove it, but it simply says that if we have bunch of chi-square distributions, bunch of independent chi-square distributions, then their sum follows chi-square, where the parameter, the r, would be just sum of all this. Okay. We'll leave it there. We'll not discuss this in more details. Okay. Finally, again, all these are I'm considering as a sort of the, as I mentioned, that there I'll be studying 3 distributions, and this is the first 2, right? So I'm done with the gamma, and I'm done with chi-squared. The final one that we'll be mentioning now is the t distribution. So let's mention t distribution. So the t distribution, it's sometimes called a student's t distribution. Okay. Just a little bit of history. So this distribution was discovered by W.S. Gossett. Okay. But he published his work as a pseudonym. So with the pseudonym student. And that's why this distribution is called student's t distribution. Okay. But it's really discovered by Gossett. It's a very, very famous distribution. So let me just mention it here. All right. So let's see. Let's consider this. Suppose the construction. Suppose W satisfies a normal distribution with 0, 1. Okay. V, a random variable that satisfies a chi-square distribution. Now you know everything. So you know a normal distribution from it's a standard normal distribution from the previous courses, and this V is satisfying some chi-square distribution that I just defined. Okay, and let W and V are independent. Okay, three things. So we have W, we have V, and W and V are independent. Okay, define a random variable T as W over square root of V over R. Okay, what are these numbers? So W is W, the normal distribution. V is V, the chi-square distribution. What is R? R is this parameter. I'm dividing by that. Okay? So it's a new random variable. Okay. This random variable is called, well, it is, let's see the distribution, um, the PDF, then the PDF of T is given by, it's very messy, but let me still write it down. It's written as G1T equals gamma. Let me just write it once and for all. So it's gamma of R plus 1 over 2 square root of pi R gamma of R over 2 1 over 1 plus t squared over R plus 1 over 2, and that's it. Minus infinity less than t less than infinity. So the PDF of this t defined this way can be shown to satisfy this PDF. Okay. This is called a t distribution. This is the PDF of t distribution. And what is a t distribution? Like I mean, in the form of the distribution, it's basically the quotient. I mean, it's basically you take W, you divide by the square root of some chi-squared and divide it by R. So whatever that is, and you may surprise or you may wonder like why do we even need this distribution? It's extremely useful distribution, as you will see later. Okay, will not work with this PDF. So I'm just putting this here for completeness, but will not really work with this PDF. But there are other ways to bypass this one. Okay, now one thing which it's important to see that remark. If I compute G1 of minus t, that is same as G1 of t. Why? Because look where t appears only with t squared term. The only term where it appears is t squared. So this is a symmetric distribution. Okay, so hence the PDF of T is symmetric about 0. Okay, all right. A couple of more things. As we have done for every distribution so far, um, what is the expected value of t? It can be shown it's 0. It's not really hard to do it. Okay, in fact, it's very easy based on this distribution function, because if you multiply, so when you compute the expected value, you basically integrate this and you multiply with t times this one, and that will be an odd function. An odd function, the integral will be 0. Uh, as long as the, I think now it's a good time to mention that this r here is called the degrees of freedom. Okay, I think I forgot to mention it while defining the character. So this r is the degrees of freedom. So let me just write it here. So for the chi-square distribution, r is the degrees of freedom. Okay, and that actually, so this r in the chi-square distribution uh, is trickling down to this r in the t distribution. So consequently, this has also the degrees of freedom r. Okay, so whenever we talk about this r, so we say that this has degrees of freedom. Okay, freedom r. Okay, now one thing is this result. Why I'm mentioning this? This is true for this is true when r is more than 1. Okay, so when r is less than 1 or something, so there are some problems with this expression. So I mean, a lot of the technical details are needed, but so I'll not go into that. But this is just note that this is true for expected value of t is 0 provided r is more than 1. Okay, let's see. What else do I need? uh, Also, variance of t is r over r minus 2, provided r is more than 2. Okay. So combining these two results, I can say that, so when r is bigger than 2, I can say that it has mean 0 and variance r over r minus 2. From now on, whenever I'm talking about this student distribution, I'll be assuming r is more than 2 and these two results. Okay, well, this is true even for r more than 1, but just to combine these two results, I'm just assuming this. Okay. Okay, I'll conclude with a theorem which will be extremely useful for our course. It's called the student's theorem. Again, it's discovered by Gossett. Okay, this will directly connect the first part of today's lecture with whatever we are doing. So by now we are done with all the distributions, but now what is the connection? So we had, I mean, we started this class with some sample mean, some population mean, some mean of the or expected value of the sample mean and things like that. So what is the relation between all those and this distributions that we just studied? Okay. So let x1, x2, xn be IIT random variables, each having a normal distribution with mean mu and variance sigma squared. Okay, so each of this x is following a normal distribution. Okay. Now define, and we have already done it. So define x bar is 1 over n I from 1 to n xi. What do we call it? We call it a sample mean. and S squared, which is what we call this a sample variance. Note this n minus 1, okay? And that's why we discussed that before. Xi minus X bar squared. This is something we have already discussed. Okay. Then, and here are the beautiful results. There are 4 results, okay? First one is X bar, sorry. We have already seen that this X bar has a mean. So we have seen this. E of X bar is mu. Variance of X bar is sigma squared over n. Okay, we know this. It does say that it has expected value mu and variance sigma squared over n. It does not say anything about the distribution. It can have any distribution with this mean and this variance. First part of the student's theorem, it says that it actually follows a normal distribution with mean mu, variance sigma squared over n. That's the non-trivial part of this statement, that we already know that mu and sigma squared over n are mean and variance, but what it says is it has the normal distribution. Okay. B, X bar, this one, and S squared are independent. So this and this are independent. Okay. Third part, and for this one, let me just show you what I wrote before. Note that we have a quantity S bar, S prime, which is sort of the intuitive definition. I called it intuitive variance, okay, which is actually intuitive sample variance, which is actually the sample variance. There is the actual sample variance. Times n minus 1 over n, right? Okay, now part C. So what I'm trying to say, sorry, I forgot to mention. So that means it says that if I have n minus 1 times s squared, that is n times s prime squared, right? So that's why this n minus 1 s squared term, you'll see it appears sometime over sigma squared. What is this quantity? Sample variance n minus 1 sigma squared. Please note that this s squared is a random variable. Okay, sigma squared is not a random variable. So this is a random variable. Basically, you can check the standard deviation of 10 students, or sorry, you can check the variance of 10 students. You can compute a number. If you find the variance of other 10 students, you'll find a different number. So s squared is a random variable, but sigma squared is the fixed number. Okay. This has a chi-square distribution with n minus 1 degrees of freedom. Okay. That's why we study chi-square. Okay. Finally, the most remarkable one, the random variable, and this will actually give you a hint, t equals x bar minus mu. What is x bar? X bar we have defined. What is mu? Mu is the samples from which, mu is the population mean from which it's defined. Over S, we know what is S, over square root of n, has a student's t distribution. T distribution with n minus 1 degrees of freedom. This is an amazing result. So that means now, later on, when we'll be studying this, we'll have some expected value of the sample mean. Please note that the sample mean x bar, it's a random variable. So now we compute this, we have the sample mean. So this is the sample mean. It's a random variable. This mu is the population mean. It's a fixed number. This s is a sample, well, s squared, square root of s squared. S means square root of s squared. It's a let me call it sample standard deviation. It's again a random variable, and n is whatever number of samples I'm talking about. So this quantity, so there are two randomness here and here, it follows a student t distribution, okay, with n minus 1 degrees of freedom. Okay, so let's see. I think that should be sufficient. Yeah, so this should be sufficient background. So whatever we have done today is first just a brief recap. So first we studied the sample mean and sample mean and sample variance, and then we paused, and then we moved on to study three different distributions where gamma is really a for studying chi-square. What I would suggest is for your purpose, just focus more on what I did for the chi-square distribution as well as the student's t distribution. And all the results are mentioned here. In the next class, we'll be using everything, what we have just studied, in order to study some statistics, meaning that we'll be studying some maximum likelihood function and other things based on this one. Okay, so that is the end of the first class, and I'll post the second class soon. Okay, let me just stop the recording.